Hello everyone, this is our first topic for A2 physics, circular motion. This is for your A2. This is the first chapter that we are going to start in our A2 classes. Now circular motion, you are quite familiar with it. You have already dealt with this chapter in your O levels, so you have a basic idea what circular motion is and what force acts on an object when it is moving in a circular path, right? So if we just go back to what we did in O levels, circular motion is basically an object moving in a circular path in any direction, let it be clockwise, anti-clockwise, doesn't matter. When it's moving in a circular path, the type of motion we call is circular motion. Examples are, the common example is the planets orbiting the sun or the satellites orbiting the planet. This is the most common example. And we have already also read a few more things, that when an object moves in a circular path, even with a constant speed, even if the speed remains constant, its velocity changes. I hope you remember that the velocity of the object changes as it moves with a constant speed. And the reason for the velocity changing was the changing direction. So you see, if the object keeps on moving in a circular path, at every point its direction is changing. Okay, so the direction keeps on changing, and since velocity is a vector quantity, the velocity also changes even though the speed remains constant. So another thing from here was, if the velocity of an object changes, we say that the object is accelerating. Okay, so the object moving in a circular path, even though if it's moving with a constant speed, its velocity changes because of the change in direction, and the change in direction and the change in velocity causes the object to accelerate. Now if you remember Newton's second law, it states that acceleration of an object requires a resultant force to act on it, right? So according to Newton's second law, F equals to m into A, where A is proportional to the resultant force. So if there is no resultant force acting on an object, there is no acceleration. That is from Newton's second law. So when we are saying that the object is accelerating, we also have to say that there is a resultant force acting on the object. So this also we have studied in O levels, that an object moving in a circular path always has a resultant force acting on it towards the center of its motion. Doesn't matter at whichever point it is, the resultant force always acts towards the center, and this resultant force is called centripetal force. So one thing which is very important to know here is that the centripetal force is always acting towards the center of the circle in which the object is moving, and this centripetal force is the resultant force acting on the object. This you have to keep in mind, okay? That centripetal force, you cannot just apply centripetal force on an object. It's not an electrostatic force, or it's not a magnetic force that you place two magnets together and there is a magnetic force acting between them. It's not that two charges you place together, you can have electric force between them, but you cannot produce centripetal force like that. Centripetal force is always resultant of some other forces. For example, when we talk about the earth rotating the sun, say the sun is here, now there is a gravitational force acting between them. The sun is pulling the earth towards it, the earth is pulling the sun towards it, right? There is a gravitational force acting on it. So the force of gravity by earth on the sun and the force of gravity by the sun on the earth are equal, according to Newton's third law, that the force applied on the earth by the sun and the force applied on the sun by the earth should be equal. The resultant of this two force provides a centripetal force. Okay? The resultant force, or the gravitational force acting between these two planets, or these two objects, the earth and the sun, provides a centripetal force. So you cannot say that gravitational force is the centripetal force. No, the gravitational force acting between the earth and the sun provides the centripetal force. So keep this thing in mind, this is very vital, that centripetal force itself is not a force, it's a resultant of some other forces acting between two objects. And this is the force which causes an object to move in a circular path, and due to this resultant force there is an acceleration acting on the object. So far what we have discussed, this is all O-level stuff that you have studied. So I guess this is just a quick brush up. of what we did, and then we will move on to the next part, which is the new thing that you will be learning. Okay, all right. So next we will be coming across a few terms which are quite new to you. That will be, one of them will be angular displacement, and the other one will be angular velocity. These are the two terms that we will be discussing today. Now, angular displacement and angular velocity, what are this? Now, we have already discussed, or we have already learned about these two terms, displacement and velocity, in our O-level classes, right? What is displacement, what is velocity, we know that. So the new word that is coming here is angular. This is the new word that we are getting, right? So what is angular displacement? Now, when we talk about displacement or velocity, what we have always learned in O-levels or in our AS is an object moving in a straight line, or the resultant of directions caused by an object moving in a straight line. Like if this was the first displacement, then this was the second one. So the resultant displacement was found like this using a vector diagram. Or if the displacement was in a straight line, first it moved in this direction, then it moved in the opposite direction. We added and subtracted them to find the resultant displacement. But now when we are talking about angular displacement and hence angular velocity, we talk about when an object moves in a circular path and how much angle did it cover from the center. Okay, so let us see that. Okay, so as we were saying, the object when moving in a circular path will have angular displacement and angular velocity. Like, let us consider an example. Let's say an object is moving in a circular path starting from point A, moves to a point B, okay, and its center is somewhere here at C. So how much angle did it move through? If we try to measure the angle, so let's say the length from A to B is S, the angle from A to B is theta, and the radius of the circle is R. So I'm pretty sure you all know how to find the value of theta from here, or how do we define theta. Theta is found using the formula theta is equals to S by R, right? Arc length divided by the radius when we are finding it in radians, right? So theta is equals to, alright, so theta is equals to S by R. So this is how we find the angle it has moved when it was moving from point A to point B, right? So angular displacement is basically, when we talk about angular displacement, it basically tells us when an object is moving in a circular path from point A to point B, by how much angle did it move through this arc length, right? So the angle is theta. This theta is basically the angular displacement. So angular displacement is the displacement of an object, but in terms of angle. Previously we used to do displacement in a straight line always, right? But now we are doing the displacement in terms of angle because the object is moving in a circular path, okay? So angular displacement is basically the angle through which an object moves when it goes in a circular path. Now if you know the displacement, we have already learned the formula of velocity before, that velocity is rate of change of displacement. So displacement divided by time. So that was velocity, which we have already learned in O-levels and in AS. But here we are talking about angular velocity. So this is for linear velocity, that's correct, but angular velocity has a different formula. So when we are talking about angular velocity is represented by the letter omega. Okay, it's written as W, but a Greek alphabet, it's written as omega. So omega is equals to how many angles did the object move through when it's moving in a circular path. So omega is given by angular displacement divided by the time it took for the angular displacement to take place. The same as this one, displacement divided by time was velocity. When we are talking about angular velocity, we are again talking about displacement, but this time we are talking about angular displacement. Since angular displacement is measured in terms of theta, so delta theta divided by delta t, which is rate of change of angular displacement, gives you angular velocity. So this velocity we used to write it in meters per second, and here, since theta is measured in radians and time is always in seconds, the unit for angular displacement is given as radians per second. Okay, so we came across two new terms today. One of them is angular displacement and the other one is angular velocity. So angular displacement, again I'm saying that angular displacement is basically the angle through which an object moves from point A to point B or from any other points when it's moving in a circular path. Okay, and that angle is found using the equation theta equals to s by r, which is arc length divided by radius. You already know this theta which we are finding here is always measured in radians, not in degrees. And then using that value for the displacement, the angular displacement, we can find the angular velocity, which is written as omega and is found using the equation rate of change of angular displacement. So angular displacement divided by time, and the unit for this one is given as radians per second. Okay, so up to this we'll keep it here in this video, and in the next video we'll talk about the other terms that we will be learning in this chapter.